Okay, so if we're going to do this inductively, then got to have your base case. So let's just start with what? I can't hear a damn thing with.
Yeah, we said it was true for the base case, right?
Okay. Aurora, you got any thoughts? Do what?
So V of x of n is equal to V of x to the n.
We don't know that. You'll have to show that. Because that statement is true if it's a homomorphism or if it's an isomorphism. So we can't assume it because we still haven't shown it's isomorphic yet. So what do we need to show for the operation preserving? Correct. Because this is what we have to show, right? Right. Myself a little bit of room here. All right, so we need to start off, with our proof. We've got to start off and say, okay, well, we've got two elements in the domain, right? And we also need to state, hey, these are our generators for U10 and U5, right? And then we just look and see what happens with this, right? So if we have those two elements, what do we do? Right. So maybe, because what I would like to have happen, we'll say that's x to the n and x to the m maybe, all right? But now as I'm writing the proof, I'm also thinking, okay, I ought to clearly state what these things are. So say, well, then maybe there exists an n and an m such that a equals x to the n, b equals x to the m, all right, since they're cyclic groups. Right. So when you do things like that, just make sure that you clearly state it out in there what you're changing variables to and, all of that stuff. But then we know that that's true. That's just an exponent law, right? And by definition of our phi, we know that's y to the N plus M. But we don't need to. Okay. Well, we have our operation preserving. We know it's 1-to-1. It's on 2. It's an isomorphism. Because that's all we were trying to get at. The whole deal with the exponents was if we knew this, it would make it easier. All right? Okay. But we didn't know that, so we couldn't use it. But we weren't, unless I'm just forgetting something that we talked about on Tuesday, we didn't need. Our goal wasn't to show this. Our goal was to show that it was isomorphic and order preserving. Continuing on the thinking about these, and I don't have enough room for this thought. What? We'll see if we'll make things crash. Oh, great, it's going to give me the whole half-page thing again. Why does Word do that to me? Oh, there we go. All right. I want to hide. I want to. I don't know. I'll just use this maybe. They just updated like 2 days ago, and I don't know. It kind of annoys me. You know, once I get used to something, I'm old. Don't change shit on me. No. So are the rational numbers under addition isomorphic to the rational numbers under multiplication? So Jasmine, if you had to take a guess, are they isomorphic or not? Well, let's have Paul. Who thinks they're isomorphic? Who thinks they're not? So only one person has an opinion? Just thinking gut feeling.
I'm skeptical of the guys. I think they're going to be isomorphic. I don't think it's going to happen. I don't think they're going to end up being isomorphic, but I'm prepared to be surprised.
Or what's your gut tell you? What about you, Jasmine? Was that a yeah? So I'm trying to force you into thinking and making a judgment without a lot of stuff because every proof and everything that we do, you have to start with somewhere, right? So make a damn decision and say, well, yeah, I think it is. Now let me see if I can show it. During that process is typically when you arrive at, oh crap, it's not, or it is, right? But a lot of issues that people have is they sit there and they stare at things and they never get over that first, well, I'm going to show that it is or not because I can't make a decision, right? Okay. So you're getting paranoid over the homomorphism part, the operation preserving part, right? Okay. So if it's operation preserving, then again, if I have some phi, whatever letter you want to use, then I have to be able to show this. Okay? Now, the one-to-one and onto, why does that not bother you? Okay? So, I just didn't know if there was a particular reason. Right. So if it were an isomorphism, if there were, then we would have to have something like this, right? So the next question is, can you think of anything in the rationals that could particularly cause us problems, irregardless of what the actual function is? Yeah, well, I left out a detail. Not including 0 for the image. All right, so think about high school algebra 1 or before. Okay. Just looks wise, okay, what is that reminiscent of? Something times something equals this other something. Okay? So I'm just thinking, what does it look like in of something that we absolutely know, okay, can never happen? Well, I don't know. I mean, to me, it kind of looks like, oh, I don't know, some number equals maybe it's square roots multiplied together. Something times something equals something else. And I'm thinking about this because we know if you square something, what is this number always going to be? Always winds up having to be a positive number, right? Now, if we have something that maps to a negative number, I don't know, is that going to give us issues? Because kind of what I'm thinking of is that we would have to have that situation. If there's a homomorphism, that would have to be true, right? Because phi of 1/2 of A, phi of 1/2 of A, okay, that's in the group with the image, but that also means that you should be able to do that because we can add them in the original group, look at its image, okay, or we could look at the images and then perform the operation in a second group. That's what the operation preserving stuff means, right? Okay, so you're either combining them before you do the function, or you apply the function and combine them afterwards, right? So when we combine them before, it's addition. If we combine them afterwards, it's multiplication. Does that make sense? So this would have to be true then, if there's an isomorphism. But if that's true, and there's supposed to be a little a there, then if something maps to the negatives, we would have to have this situation, which would mean there is something squared equal to a negative number. That's a problem, right? So it doesn't matter what function we pick, whether it's one-to-one or onto, doesn't really matter, okay? Because it can't happen, right? If it's a homomorphism, if it's an isomorphism, this is the situation that arises, which means it's not onto, because nothing can map to those negatives. And if it can't be onto, it can't be an isomorphism. So the problem, I think this is kind of neat. The problem is we can't even get onto. Okay? But to show that, we have to use this idea, well, if it's an isomorphism, we have this property. This is the property that screws things up. Okay? So while we're using the idea of it being order preserving, or operation preserving, we haven't shown that it's not, but we've shown that if it is, then it can't be onto. And then if it's not operation preserving, then not an isomorphism either, right? So no matter how we go, we arrive at some kind of issue. Most everything in 308 and 408, okay? Most everything in modern algebra will boil down to the high school algebra and below. And that's the point of it, right? Okay? I mean, the point of modern algebra is to take what you've already done with integers and real numbers and rational numbers and say, you know what? This is what's in common between all of this stuff. Okay? These are how everything's kind of put together. And then if we can think of it in this abstract manner, then I know it's true for all of that stuff. I don't have to go back and kind of verify it for integers, and then for rational numbers, and then for real numbers, and then complex numbers. All right? So on a lot of these things, I draw a lot on basic arithmetic, basic algebra, because all of the stuff that you've learned still applies, right? I think of them as examples of what we're doing now. Okay? So I think it's important to sometimes just draw back and think about those. And then, so yeah, I mean, when I see something like that, I think, well, I mean, is that something that's familiar to me? Does it look like something? Because that might give me a hint on what to do. Right? All right. So these are all of the properties for isomorphisms and stuff. So of course, identity goes to identities. Here's our great property we were thinking of that we kind of got hung up on thinking about, right? Some stuff about commutivity. So of course, if it's isomorphic in a billion group, the image has to be in a billion group, right? That's kind of an if and only if thing. Maps generators to generators. Right? You know, if you have cyclic groups and stuff. Preserves orders, all of that stuff. So when we start talking about isomorphisms and rings, of course, all of this stuff is still going to have to hold. We're just going to add some things to it. Okay? But what were cosets? So a coset, remember what we do is we take a subset, okay, of our group, and then we say, okay, well, let's start multiplying everything in that group, each element in that group by all the stuff in that set, okay, and see what happens. Right? So, I mean, the easiest one that's kind of analogous to it would be thinking about, okay, that our group just be simply the integers, okay, and let our set be all the multiples of 3. All right, so we have to have a group, we have to have a set. And then we take each element in the group and we multiply it by all of the crap in the set and we get a new set, right? So, or we add, let's do it with addition, okay? So our group is the integers under addition. So you have to start somewhere. So you just pick any old element. I'm just going to pick 0 because it's just an easy place to start, right? So if you add 0 to all of these multiples of 3, well, we're still going to get exactly that same setback. 6 and 6 is the next one. That's awesome. Da, 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 da. So 0 plus 0, 0 plus 3, 0 plus 6, 0 plus 9, 0 plus 12, right? And they say, okay, well, that's all of those. How about what happens if we add 1 to all of those things? Well, I'm going to have a harder time writing out with plus or minuses since that's going to line up. But 0 plus 1, 3 plus 1, 6 plus 1, 9 plus 1. And then go in the other direction, of course, we'd have negative 3 plus 1 would be negative 2. Negative 6 plus 1 would be negative 5, blah, 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 blah. And that gives me another set. Then we look at 2 plus h, right? Add 2 to everything in h. And negative 1, and negative 4, 7, blah, 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 blah. And then we would have 3 plus h. Now, if we do 3 plus h, Well, 0 plus 3, 3 plus 3, we just see we wind up with exactly the same thing we had with 0, right? So now we're just going to start repeating ourselves. So then these are our cosets. Yeah, H will always wind up being a coset because you're always going to have the identity plus those, right? And the identity, when you add it to anything, doesn't change those. So H will always be one of the cosets. Now, there are a lot of special things about cosets, about how it partitions the groups, okay? Which means you're going to get, in between all of those, every element in the group, right? Okay? There's no intersection between the cosets. There's no overlap. If there is any intersection, then they have to be the same. Okay? So as a result, we will often use notation for these. It says, we'll call this one 0 bar, or 1 bar, 2 bar. Okay? And that 0, 1, and 2 are the representatives of that coset. We could pick any number in it. So 0 bar could be the same thing as 3 or 6 bar or whatever. Okay? Now, anybody remember what happened if H turns out to be a normal subgroup? What could you do with those? Yep. Okay. Yeah, so we can make these quotient groups, okay, like Z mod 5. Okay? That's good example stuff. So we could use these ideas of cosets, say, okay, and now we have these specific kind of cosets, these ones that are formed with normal subgroups, and we could take a group and form a whole new group out of it, right? Okay. So we're going to be doing, again, similar stuff with rings and ideals and things like this, these modules. There's all kinds of neat analogies of things that you saw in 308 that are going to have the same type of thing with the rings, okay? So we're talking about subgroups and factor groups and stuff. In relation to cosets, if H is a subgroup, then of course we had all of these properties. A is of course an element of coset formed by AH. AH is equal to H if and only if A is an element of that. Number 3, it kind of looks like an associative property type thing, right? But if you took 2 elements and you looked at their product, said, okay, well, that product is in this coset, then you look at the coset formed with one of those factors, and then take that coset and add it, take this other element and add it, you're going to wind up again in the same spot, okay? Intersections are non-empty, blah, 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 blah. And then if we had the normal subgroup, that's where we got our factor groups, okay? Can you think of any good examples of factor groups? That is the laziest example ever. All right, now, any restrictions on what n needs to be?
Gotta be an integer.
And that's pretty much it, right? All right. Now, speaking of this, with this one is, we know the integers are cyclic groups, right? Okay. Are the factor groups also cyclic?
I'd say so,
Okay. The original group was a billion. Well, the factor group's always going to be a billion. Yeah. I mean, if you can add in any order, and then you look at a subset of the integers, they're still a billion, right? You're still talking about adding integers to other integers, really. So, now, how about, can you think of any example that's not a trivial example? Or how about a non-abelian example? Let's get even further. How about a non-abelian example of a factor group?
What's the definition of a normal subgroup?
It is a subgroup that's commutative. Yeah, so it would be a subgroup, right? But in that set, you can multiply elements or add elements in any order you want. That's not necessarily true of the entire set. Okay? But it's like we take this big old lump of numbers here and say, okay, well, it's not commutative. Okay? But there are certain ones in here that are. So we peel those out. If that's a subgroup and commutative, that's our normal subgroup. Make sense? All right, so first, what kind of non-abelian groups do you remember? Oh, dihedral groups. I like the dihedral groups. Okay? So, I like them enough, but let's be really lazy and let's go with like D4. Okay. All right. So if you think about the dihedral groups, remember that's the symmetries of a square, this one, right? So you could rotate it 90 degrees. You could flip it over a horizontal axis. You could flip it over vertical and horizontal axis and the diagonals as well. Do y'all remember those? Right? Okay. So, do you remember a normal subgroup of the dihedral?
The cyclic subgroup by the 93.
That we saying? You said 90-degree rotation, right?
Yes.
All right.
But only
Hold on.
one is the subgroup generated by.
So that would be all of those, right? Rotate it 90 degrees, 180 degrees, 270 degrees, and then you're back to the beginning. Okay? So is that a normal subgroup? And if we form this factor group, what does that mean? All we're doing is looking at all of the cosets right? And those cosets are the elements of the group. So of course we would have H would be one of the elements, right? Now, that takes care of all of the rotations. So then we would have to say, okay, well, what about when we have, all right, I'm going to change this to a K just to stick with common notations that you might have seen and stuff. Because H was always the horizontal thing in that group, right? I don't want two H's running around. So K would be one of the elements. And then we say, okay, well, what happens when you take H, the element H, and multiply it by that subgroup? Okay, so you would have H. Now, what do you get when you're looking at H opposed with R90? Do y'all remember how to multiply elements in the dihedral groups? Do what now? But we're talking about a rotation and a flip over an axis, right? Okay. All right, so just because of room. So remember, the elements of the group here, okay, are functions. We're taking an object and we're doing something with it, right? We're rotating it, we're flipping it, we're changing it, something else. These things are functions, okay? The identity function is just leaving it alone. Right, then we have the element R90, and what does that do? That switches and it rotates everything 90 degrees. By convention, yeah. All right. Does it have to be? No. Okay. Now H is flipping this sucker over the horizontal axis, right? If I flip that over the horizontal axis, I get a square where there's those vertices, right? If I flip it over the vertical line through the middle of it, and then we could flip over the diagonals. So this one I'm going to call D, and this one is D prime. And that did not show up. Let's see. It's blue. So we're going to call flipping over that one D, flipping over that one D prime. All right, so those are all of the elements of the dihedral group. Okay? Now, if I want to compute then R90H, well, I think I had written down first HR90, all right? R90 says we're going to rotate the object 90 degrees. Then H says we're going to flip over the horizontal axis. It's composition of functions, right? When we compose functions, what direction do we go? Right to left. So I'm going to do the rotation first, then I'm going to flip over the axis, right? So if I draw it out in 2 steps, my first step say, okay, well, I'm going to rotate this thing, and now I'm going to have that square. Then I'm going to go with that horizontal axis, and I'm going to flip that thing over, and that's going to give me DACB, and then I just need to compare and that was D prime, right? So when I multiply those things, I get D prime. So that's going to be in that coset, right? And I need to do the same thing. If I rotate and flip over, I want to compute where am I at? H with R180. Now, we know it's non-commutative, so before I move on to yet other ones, what happens if we do R90 composed with H? Or, do what? So if we flip it first, then we rotate it 90 degrees, like it's AB. That was element D, right? R90. Yeah. Now, if it's R180, what do we get? So we would have our square there first, rotating it 180 degrees, then flipping it over the horizontal. You would get that. Huh? Yes. All right, so will we spend a whole lot of time? We would wind up with D in here, V prime as well, I believe. V prime. I don't know. A D prime, V prime. I don't. So here we have 2 elements, because that takes care of all of the stuff in there, right? So here we have a factor group, and that group only consists of 2 elements. the rotation and that flip with those sets, right? But that does form then a group. It turns out to be a pretty trivial group, but hold on. Hello? Okay. All right, I'm in class, so let me call you back. I was just making sure there wasn't something going on. All right. All right, so anyway, we can form groups by doing this, right? We're going to do the same thing with rings, of course, okay? But, of course, they're not factor groups, okay? We'll be forming, modules and stuff using these different ideals and stuff. We've talked about homomorphisms, and that stuff's the same, so. All right. So I guess my question then is, for all this stuff, let's define a ring. Let's get started on that. Because rings are just cool. Ah, shoot. All right, so here's all of our properties that we have to have for a ring. Does it say it is? Nope. Okay. Now, if it is, then that's what we call a commutative ring. Okay? So if you see a commutative ring, that means the multiplication is commutative. Okay? All right, so in a nutshell, we have all of these properties. What do these properties tell you? Yeah, we're starting off with an abelian group. Okay? So we're really only adding two little things to what you've already done, right? Okay, so it's an abelian group under addition. It is not a group under multiplication, because we only have these two stipulations about the multiplication. It's associative, and we have the distributive property. Okay? There's nothing that says we have a multiplicative inverse. There's nothing that says we have an identity for multiplication. There's nothing that says anything about multiplication other than it's associative and we have the distributive property. Okay? So we're adding the second binary operation, the multiplication, okay? And we're adding these two conditions to the fact that we have this other structure in that. Okay? Please don't make any assumptions about the multiplication and stuff, because that's the trap that most people fall into. They start thinking it's a group under multiplication, and it's not. Okay? Because there is no guarantee of these multiplicative identities, things like that. Okay? However, I think it's kind of interesting. Why an abelian group instead of just a group? I mean, abelian seems a little bit arbitrary to me. Okay? We just spent the whole class talking about groups, and we stress so much. You know, not everything's commutative. You know, we've got all these non-commutative groups. And then we define this other structure that's based on those ideas and say, it's an abelian group. Okay? And that seems a little bit odd to me. Okay? But here's what happens. This statement right here forces it to be an abelian group. There's no choice. Let's just think about using the distributive property. Okay? Now, I have an additive identity, stuff like that, so I know I have a 1 that I can add to a 1. All right? Or, not identity, but... if we have a... Let's just start off with this one. If we have a multiplicative identity, we have a 1. Okay? But our distributive property says we can do this. Right? We take whatever element's in front, we multiply it by each of the ones in the parentheses. Which would really turn out to be this. However, it's also distributive over the other direction. Right? So, by the same token, we would have that. Take those C's off, we can subtract the B's, and what's left? B plus C equals C plus B. Under addition is commutative. Now that's if the ring has the identity. Okay? Now, that's the motivation for having this defined within a billion group. Because we don't necessarily want to define a ring and then not be able to have an identity. Right? Okay? Because most of the rings that we deal with have identities. Up until this point, we're talking about integers and real numbers and all of that stuff, right? Okay? So the motivation, the thing with modern algebra is to explain all of this other stuff that we know. Well, let's not define something that rules a bunch of that out. So having it in a billion group isn't just an arbitrary thing. There's a reason that we define it that way. Okay? Now, if we leave out the abelian part, could we get another structure? Yeah, I'm sure plenty of people have studied stuff like that. Okay? Now, do I know the names of what they call it? I mean, it's probably a semi-ring or something like that. Okay? Just like we have semi-groups and, stuff. So there is a reason for picking it to be a billion, and that's one of the reasons. Okay? So we've got some good examples then, right? That we already know. The integers. Right? Now, we have the normal, addition and multiplication. Now, keep in mind, just as with groups, when we talk about addition and multiplication, that doesn't mean your actual addition of whole numbers, multiplication of stuff, right? Because when you add and multiply ordered pairs, that's not just the same as doing 2 times 3, right? Okay? So we use the addition multiplication terms fairly loosely. There's 2 operations. Okay? All right. But other special things that are in these things, since we're already talking about it, the integers under our normal multiplication and addition, okay, does it have an additive identity? Or what is its identity? All right? So the additive identity is 0. Does it have a multiplicative identity? So the multiplicative identity is just 1. Now, there's a fancy name for that. It's called unity. Okay? So if you see a ring with unity, that means it has a multiplicative identity. Okay? Because, we like fancy names. We also like to confuse people by having names of things that are very similar. Okay? So you will also see something called a unit. Okay? This is the fancy name for has a multiplicative inverse. Because not everything has a multiplicative inverse. For instance, in the integers, 2 does not have an inverse. Right? Because to have an inverse, you need whatever integer times whatever its inverse is. I don't know why I called it e, but whatever. Has to equal the identity, right? So if you look at 2, 2 times what equals 1? Nothing. Not in the integers. Okay? So the only units in the integer are 1 and -1. Do it. Okay? So in the integers, those are our units. All right? Saying it has unity just means it has a multiplicative identity. Okay? since we're talking about multiplication and stuff like that, what does it mean when we say A divides B? So Gavin, what's that mean? No, no, you're not allowed to use the word divides or divisible or. Okay, so now, two divides 6, right? You could say 2 is a factor of 6. How would you prove that it's a factor of 6? Now remember, we only have 2 operations, addition and multiplication. That's it.
Show that you can multiply with something 2 equals it.
And what would you multiply it by? 3. So we say, oh look, 2 times 3 has to equal 6. Therefore, 2 is a factor of 6. 2 divides 6. Okay? So when we talk about divides, what we really mean is there is something we can multiply it by to get that number. Okay? But that's really wordy, right? Okay? But when we say that A divides B, what we mean is, now I use very few symbols from logic, but there exists is one of those. And that's what that means, right? The little backwards E is there exists. Okay? So there exists a C in our ring such that A times C equals B. Notationally, we'll put a vertical line between them. A divides B. And if it doesn't, of course, the negation of that is A does not divide B. Now, to confuse things just a little bit further. We love to confuse things, right? We want to make you think, okay? Right. N times A, where that is an integer. This comes from the ring. Means exactly what we've always taught multiplication means. You're adding that ring element n times. Why are you, what is wrong with you, you stupid thing? I want the little, there we go. There's n summons there, okay? Now, so that is subtly different. We're not talking about the multiplication in the ring. We're talking about the repeated addition. So it's always an integer times that. So you need to be real careful sometimes about the context of things, okay? We can, to differentiate between the two of those, okay? Well, yeah, I'm just going to change color then, too, while I'm at it. What the hell? Okay. Let's say that we have polynomials, okay? Any polynomial with, let's say, integer coefficients, okay? We just use whole numbers for the coefficients, okay? If we take that is in our ring, okay? and we multiply, so this is like A, and let's say our thing B is -1 plus x1 minus x2. Let's say we just those two, okay? Now, when I define addition, it's going to add polynomials. When I define multiplication, we're multiplying polynomials using the distributive property and stuff, right? Okay? But then if we did something like 3a, so the ring multiplication AB is just your typical multiplication where you distribute everything out. Okay? Two A now here that actually matches up with, if we think about 2 as a polynomial. All right, we get the same answer, so there's no issues, okay? But that's because of, well, how we define the multiplication here, stuff like that. It's always kind of not guaranteed that the things will match, okay? You want to be careful. The biggest warning I have is with these rings, is this. Since we're talking about multiplication and stuff, and division, okay, we are not guaranteed inverses, which means we do not have cancellation laws. Just because you're multiplying the same thing doesn't mean you can divide both sides of the equation by the same thing anymore. Okay? I mean, that's been a lifelong rule, right? Got an equation, you can divide both sides of that equation by the same thing. No. Cannot do that. That might be one of the most common mistakes that people will make. Okay? So be very cautious when we work through things, we're solving equations and we're doing other stuff with these rings. You cannot guarantee that you can cancel out with the multiplication. Okay? 9:30 to 10:45, right? 10:45? Okay, so we're done. All right, have a wonderful afternoon and a good weekend and all of that stuff. Yeah, I'm going to get the actual book today, and I'll get the first homework assignment out, so that way we've got plenty of time to look ahead at it and stuff like that. So be looking for that. I'll post it like in Blackboard or something this weekend. Yeah, I haven't even started the syllabus, but I swear to you I'll have it by Tuesday. Okay? I didn't promise I'd have it for today, but I promise I'll have it on Tuesday. I'll get the syllabus done over the weekend.
Please sign this for me. I called them the other day and they said they don't even have it.
It's probably on my desk at home then. I mean, I trust them, you know, I mean.
Yeah, I know. It's fine. All right, thank you.
So there you go.
Thanks, Bob.
Oh, you're not going to let me stop recording? Stop.